Okay, talking about circuits. So by the end of this lesson, you'll be able to describe what voltage, resistance, and current are, and describe how those three are related in Ohm's law. So you just made a light bulb turn on. Well, let's talk about it. So when you were trying to make the light bulb turn on, what was kind of the driving thought? I need to do what? What was the strategy? What were you trying to accomplish other than light? Like, how are you trying to get the light bulb? What strategy did you use? You needed to make a circuit. Yes. Okay. When we talk about circuits, like a workout circuit, that's like a loop or a path. Look at that. Same thing here. We need, like this light the light bulb. No, not light the light bulb. So, here is how a light bulb is wired. Okay, so there's a distinction between the side casing and then there's an insulation and then the tip. Okay, this is called the filament. So in order for the light bulb to turn on, you would need to connect it like this. One wire going to the tip and the other side, or the other going to the side. And now you have a complete circuit, complete loop. Good with that? Okay. So, the distinction between the last chapter, static electricity, and circuits is this. And static, the word static means still. Like not moving, you're stationary. When electrons did transfer, it was in surges or bursts, like circuits. It's a continual flow. All right with that. And one very popular analogy that we use for circuits is water flowing through pipes or hoses or something like that. Okay. So voltage, electric potential difference, is the biggest idea that we're drawing from last chapter. Okay, so it's really important that you've got it locked down on that one. So electric potential difference is the comparison of crowdedness from one spot to the next. Okay, it's the thing that motivates the flow. It's the push. It's in the water analogy, it's the pressure. Okay. So if I had in a pipe of water, if there was like 100 psi over here and 100 psi over here, where would the water flow? You're like, it's under pressure, but if I had 100 over here and 60 over here, which way would the water flow? Go to from a high pressure to a lower pressure. There's a difference in pressure. The difference in pressure would be 40 psi. That would be analogous to the voltage. There's a difference in pressure. Okay with that? And so if you had 100 here and then 20 over here, it'd be much more motivated to go to the lower because there's a difference in pressure of 80 psi. Good with that? Yep. So that's voltage. Okay. Remember in chemistry where they told you an electron would orbit around the proton or the nucleus, like the Earth goes around the sun, like orbitals. type thing. Okay, and then later on, they're like, just kidding. That was just a simple model to help you understand it. It really is like an electron cloud. Okay, this is my simple model of a battery. It's not really how it works, but it's a good model. Okay, so in our battery, we have this impenetrable wall between the positive and negative side. On the negative side, packed out with electrons. Positive side, not so much. If you were an electron, where would you rather be? Positive side or negative side? Positive side. So do you see how there's a difference in electric potential from one spot to the next? Okay? So there's motivation. So if you gave that a path to go, would you take it? Yep, electrons like, woo! And the light bulb happens to be in that path, and so bing, turns it on, and you get a flow of electrons. Good with that? Okay. Does anybody know what the voltage is on a D-cell battery? 1.5 volts. Anybody know the voltage on a C battery? Also 1.5 volts. Double A, 1.5 volts. Triple A, also 1.5 volts. Why do we have so many different sizes of batteries? That seems stupid. It's all the same. What's the benefit of having it big? It's more electrons. This will last. This guy will last longer. You okay with that? This would not go so well. Chunky. It's like, but they last longer. Cool with that? Okay. So, does anybody know the voltage on a car battery? 12 volts. Anybody know the voltage of a 9-volt battery? 9 volts. Yep. Anybody? The outlet the voltage across the outlet? 120. We talked about that last chapter. Good with that? So a little distinction there to what we're playing with. All right. Tell your neighbor. Correct answer is C. Everybody okay with that? There is no motivation. There is no difference in electric potential. Equally crowded. They're like, why would I want to go over there? All right with that? Okay. So, in reality, what takes place in a battery is a chemical reaction. If you were in honors chemistry, you did like a voltaic cell or a salt bridge. Like that is the essence behind a battery. You have a chemical reaction where one side, one chemical likes the electrons more than the next, and they're separated, and so electrons need to travel to get to that other chemical. So that's what's going inside of a battery. But, okay. So in chemistry, do you guys study, you remember studying like a reversible chemical reaction, like some chemical reactions are reversible? Okay. So B is the right answer. When you plug it up, when you put your battery into a charger, that is the motivation for the chemical reaction to reverse, go backwards, and so you have this rechargeable battery. Good with that? All right. Current. The variable for current is a capital I. I don't know why. It just is. The equation for that is amount of charge transferred over how much time it takes. So the rate of charge going by a certain point every second. That's the delta Q over delta T. The unit of current is an ampere. Short for amp. So this is different than the amp that you plug your electric guitar into. That would be an amplifier. This amp is short for ampere. The abbreviation for the symbol for amps is a capital A. So the unit where that comes from, what's the unit for charge? Coulombs. And unit for time, seconds. That is equal to amp. Coulombs per second. Make an amp. Good? I'm just going to tell you this one. Correct answer is B. Beautiful butterflies. What current measures is how many electrons go by a certain point in a wire every second. Okay? If you were hired by the Department of Transportation to measure the current of I-65, one way you could do that would be stand on an overpass and count how many cars go by underneath your bridge every second. 1, 2, 1, 2, 3, 1, 1, 1, 1, 5. Okay? That would be measuring the current on I-65. Is that okay? Good with that? Question. Is it possible for fast-moving cars to have the same current as slow-moving cars? Tell your neighbor how that would be possible.
Like if there's no space between you need slow cars, slow cars, slow cars. You have a bunch of fast, the fast wasn't more split out, the cost of the
Okay. So you could have fast-moving cars really spread out. 1, 2, 3. You could have slow-moving cars close together. 1, 2, 3. Same current, different speeds. Okay, so it's not a measure of speed, but it's a measure of how many are going by. We actually measure current in rivers the exact same way. We don't look at water molecules and say, wow, with a radar gun, how fast are they going? We measure it in cubic feet per second, how much water goes by a certain point every second. Okay, you all right with that? I know you're just guessing on this one, so I'm just gonna tell you. Okay, so you turn on a light switch and boom, the light turns on. Like, wow, those goes fast. Okay, here's an analogy. Springtime, you put your hose on your spigot for the first time, you turn on your water, how fast does water come out? Takes a long time, right? You gotta wait for it, like, oh my goodness. So then let's say you turn off the water after the water's coming out, put your thumb over the end of it, and then you turn the water back on and let your thumb off, how fast does water come out? Right? Is your conclusion like, whoa, the water's going the speed of light? It was like instantaneous. It just bumped out the next guy who was sitting right there. Does that make sense? So when you buy wire at Menards or Lowe's or wherever, it comes pre-filled with electrons. When you turn on the light, it's just bumping out the next guy. Does that make sense? It's like having a hose pre-filled with water. It's just instantaneous. They should probably advertise that. I mean, it's like, hey, electrons included. They're like, oh man, it's a good thing I didn't know where to get electrons. Yep. Good with that? So, the question is, how fast do they travel? So, the life of an electron is a pretty rough gig. So there's this crystal lattice of all the all the nuclei that these guys have to navigate through. It's a rough gauntlet. And so an electron is going like, okay, it's a violent life. Okay, they go really fast between collisions, but how quickly they go this way is called electron drift, and that's somewhere on the order of millimeters per second. Pretty slow. Good with that? All right. Connect this together, complete circuit. Electrons are going to go out. Out of negative into positive, yes? Okay. You talk to any electrician, you say, hey, what's the direction of current? They will tell you out of positive into negative. And you're like, what? All of them will tell you this, out of positive into negative. If there is one thing in physics that I could change, it would be this discrepancy here. Okay, where did this come from? Well, Ben Franklin was not only our No, he's missing the chance to like. um, Not only was he a founding father in our nation, but he was also a founding father of electricity. And he had this theory, like, hey, I bet you there's these small, like really small particles. They're charged different, and they're responsible for electricity. He had a 50-50 choice, positive or negative. He was an optimist, and so he was like, positive, things are flowing. And so science was built around this idea that positive things are flowing. Well, later we're like, hey, electrons, oh, they're negatively charged. Like, oh, well, you know what? Everything we've done so far works out great with this idea that positive things flow. Why should we change it? I mean, there's so many textbooks to change. They're like, if it isn't broke, don't fix it if it ain't broke. I'm like, it's broke. But they're like, nah, it works fine. And so we just continue on with this idea that positive things are flowing, but nothing actually goes in that direction. It's only electrons going out of negative into positive. But we say that they're positive. It's like, and so you guys get the short end of the stick of just like being able to like deal with this. And yeah. So one year I was like, you know what? I'm going to overthrow this. This is absolutely ridiculous. And so I taught everybody electrons out of negative into positive. And then they would come back to me from college like smiling. My professor mocked me profusely for that. And so where I'm landing on is I'll teach you the truth, but here's what they want you to say. Okay? So if I ask for what's the direction of current, you will tell me out of positive into negative. If I ask for direction of electron flow, you'll tell me out of negative into positive. Okay? Apologize. That's just the world we live in. Favor? The correct answer is B. Out of positive into negative. That's direction of current. Electron flow would be clockwise. Out of negative into positive. Okay. All right, the third layer is resistance. This one's kind of nice. The variable for that is capital R. The unit is an ohm. The abbreviation of the symbol for ohm, this one's fun. This is capital omega. Capital omega. You're gonna have fun right now. Okay? So resistance, that speaks to like insulators, conductors. So in elementary school, they would say, okay, you've got a conductive box and you've got an insulator box. But in reality, it's a spectrum. Like low resistance is a good conductor. So like gold is a really good conductor. Silver, and then copper, and like steel, and then like salt water, and then like wood, and then plastic, and then rubber, and ceramics or something. Like it's a spectrum rather than a binary on-off. Feel that? Okay. The circuits, we like to draw diagrams that are just shorthand. It's easier symbol-wise. So a battery in a schematic diagram is going to look like a long, like two parallel lines. The long one with different lengths. The long one is the positive side, and the short is the negative. That's the battery. The way that I remember that is a positive symbol is 2 sticks, so it's longer, whereas a negative is just 1 stick. And a resistor is like kinks in a hose. So the way you would draw this circuit here, you have battery, these are wires, like the light bulb is the resistor. That's how you draw that circuit. Okay. Remember how last semester we were like all about free body diagrams? This chapter, these are going to be our, like, circuits are going to be our diagrams. Yep. Okay, Ohm's law. This brings all 3 of these together. So, voltage is equal to current times resistance. As much as you used force is equal to mass times acceleration last semester, voltage is equal to current times resistance, V equals IR. We used this chapter. Okay. Mathematically, it's easier to do this, but conceptually, it's easier explained, rearranged like that. Okay. Voltage motivates flow of electrons. It's the push, the pressure. Resistance resists flow of electrons. You see the conflict of interest there, the battle. The result of that battle is flow of electrons, is the current. That. So, tell your neighbor what would need to happen to voltage and resistance to make current high. Make a lot of current. Tell your neighbor what would have to happen to resistance and voltage. Okay, hopefully you said you have a high voltage and low resistance. Good? Okay. So, current, most people have a fairly good understanding of that. That's not too bad because you're thinking like current in a river, flow of electrons. Voltage is the one that gets all convoluted because you don't really like, Okay, so voltage. This is the difference in pressure. This motivates, pushes electrons. It does not flow. Okay. pushes. Difference of pressure from one spot to the next. Okay? The preposition we use for voltage is across. So it goes like the difference of pressure across from like 100 psi compared to 20 psi. What's the pressure difference across these 2 points? Okay. Tell your neighbor. Correct answer is A. You have to have voltage in order to produce current. There has to be motivation in order to make the flow happen. Okay? Here's some terminology here. Potential drop or voltage drop is part of the wire that takes energy away. So voltage talks about energy per electron and the change in that. So it's like what part of the circuit is taking energy from the electrons and converting it into some other type of energy. That would be primarily the light bulb. So across B to C, that would be your voltage drop. Okay. Versus your voltage gain or your potential gain, this is the part of the circuit that gives energy to the electron. Okay, there's a certain amount of energy per electron, and if we looked at this circuit as a loop, the battery gives it energy, the electron's energy. So we would say from D to A would be part of the circuit, the part of the loop where there's energy given to the electrons. Voltage gain, okay? Just gonna tell you, you'll be guessing. Correct answer is D, dangerous dinosaurs. So, here's the deal. I'm gonna use your understanding of rivers. Okay? In a river, the current is the same at all points. Okay? Because if it wasn't, if there's more current going in than going out, you'd get flooding. If there's more water going out than coming in, you get this like dried up, like where'd the water go? But whatever comes in has to go out. You okay with that? Okay, so if we think about like different parts of the river, how would you describe the riverbed where the water's moving fast? Shallow or narrow. You gotta get a lot of water moving by this point really fast. Where do you, like where are the slow parts? It's really deep and wide. Same amount of water is going by every second. Good with that? Got a worksheet. It's due tomorrow.